Welcome to today's lesson. I'm glad to have you here. We have today dimension of physical quantities. Remember in our last lesson, we discussed about the base quantities and their units, as well as derived quantities. But today I want us to look at the dimension of these quantities. So, by the dimension of physical quantities, we mean how derived quantities are related to base, or either we can call it as basic or fundamental quantities. So we want to look at how these derived quantities, how they are related to the basic quantities. Remember, there are 7 basic quantities we listed in our last lesson, which include, we have the length, the mass, time, we have the temperature, we have current, we have light intensity, and we have substance, the base substances. Now, the derived quantities will now depend only on 3. So we are going to look at these 3 quantities: the mass, the length, and time. So, apart from the other 7 quantities, every other quantities we have are related to these 3 dimensionally. Now, the mass, by dimension, the dimension for mass is capital M. What is the dimension for mass? We're not discussing the SI unit. Of course, we know that the SI unit is kg. But by dimension, we want to represent them. So these are the base quantities. These 3 are the base quantities. The dimension for length is capital L, while the dimension for time is capital T. Now, we want to look at how every other quantities relate to this. For example, we have the first one, example 1. We have area. Area is length times breadth. So, for the sake of this lesson, everything measurement, whether distance, whether displacement, length, all of them are represented by L. Time, we have this, and then mass, we have this. So, since this is area is length times breadth. Now, length is represented by the letter L, while breadth, which is still length, also represented by this. Therefore, length times length will now give us that the dimension for area is L times L, which is L squared. So this is the dimension for area. Number 2, the dimension for volume. The dimension for volume is, of course, the first thing we do is to express the formula. Expression for volume is length times breadth times height. All these, they are all lengths. So this one is measured in L, this one is measured in L, and then this one is represented by L. Therefore, the dimension for volume is L times L, which will give us L cubed. Number 3, we can have speed, which is represented as V. Speed is expressed as, the first thing you do, the formula. It is expressed as distance over time. Now, the dimension for distance, just as we said, is L. Dimension for distance is L. Dimension for time is capital T. Therefore, we can now have L. This is L. This one, we take it up. If we take it up, now in dimension, it is what, knowing that in dimension, we don't have anything like LT like this. No, we must bring it up, please. So we now have, for us to bring T up, of course, this can serve as a quality sign. Before it comes up, the sign will change. So we now have T raised to the power minus 1. Let's write it well. T raised to the power minus 1. Okay, so the dimension for speed is LT raised to the power minus 1. This is number 3. Now, the fourth one, of course, velocity. Let us look at velocity. Velocity is expressed as displacement all over time. And of course, displacement is just distance measured in a specified direction. Now, this displacement, since it's distance, we express it as L. Time will have this, and then, of course, we'll bring T up. If we bring T up, we now have L T raised to the power minus 1. Because of that, we can now have that speed and velocity. They have the same dimension. We use them interchangeably also. But the difference between them is that speed is a scalar quantity, while velocity is a vector quantity. Now, we can have the fifth one, acceleration. Acceleration is expressed as velocity over time. Remember that velocity, of course, velocity is distance or displacement over time. Everything is all over time. So this one will now give us distance L for t. We'll have, of course, if we send it up, it becomes minus 1. All over, remember, we still have this one here, all over t. Now, for us to take this t up, we'll still have L t raised to the power minus 1. If this one comes up, dot or multiplied by t raised to the power another minus 1, which will now give us, of course, we cannot leave it like this, we'll bring them together. L t minus 1 plus minus 1 will give us minus 2. Because of that, acceleration is Lt raised to the power minus 2. Now we can have another one, the sixth one. We can have force. We have force. For us to derive the dimension for force, the first thing we do, express the formula. Force is mass times acceleration. Mass times acceleration. Remember, mass is represented as capital M times acceleration. Of course, acceleration, which is what we have already. We have already gone through the process, so that meaning we lift it. So we have Lt raised to the power minus 2. In other words, the dimension for force will give us M Lt raised to the power minus 2. So this is the dimension for force. We can also have dimension for momentum. Number 7. Momentum. Momentum is expressed as mass, is a product of mass and the velocity. Mass is written as capital M times, we have gone through the process of getting velocity, so we lift it. L t raised to the power minus 1. Therefore, we now have that dimension for momentum is M L Okay, we can have another one. Density. We can have density. If we have density, which is expressed as mass over volume. Mass over volume. Remember, mass is given as capital M, all over volume. We have gone through the process before, so volume is expressed as L raised to power 3, L cubed. Now, we bring this one up. If we bring it up, we have mass here, L raised to power. Of course, once it comes up, the sign changes, because here is positive 3. It will now change to negative 3. So, this is the dimension for density. Okay, we can now have the last but not the least. We have pressure. We can have pressure. Pressure is expressed as force all over area. Force over area. Remember, it's either you go through the process one by one. In fact, it's advised that you go through the process step by step. Because the process is still on the board, I will lift it. For force, I will lift it. Force is expressed as mLT raised to power minus 2 all over area. Area is L raised to power positive 2. Now, I'll bring it up. If we bring it up, we now have mL. Remember, this L is raised to power 1. It's still raised to power 1. Then T is raised to power minus 2. Dot this L here, if it comes up, it becomes minus 2. Now, we now bring it together. If we bring it together, we now have that the dimension for pressure is mL. Now, this is 1. 1 minus 2 will give us minus 1. And then T raised to power minus 2. So, this is the dimension for pressure. M L raised to power minus 1, T raised to power minus 2. There are other quantities. But having done this one, please, you will do this for me. So, let us give ourselves some assignments. So we can have these as our assignments. Okay, so derive the dimension of the following. Derive dimension of the following physical quantities. Physical quantities. Number 1, help us get the dimension for weights. Dimension for weights. Number 2, help us get the dimension for help us get this. Dimension for weight, dimension for work, dimension for moment of force, and dimension for impulse of force. Now, I will help you with this. Moment of force is force times perpendicular distance. Force times distance, let me use the word D, the letter D. Force times distance is moment of force. So, having given you the formula, I expect you to get the dimension. Now, we have the fourth one, the impulse of the force. Impulse of force is the product of force and time. So, help me, you can always get this one. Wait, I'll think I've given this one. Let me still give this one. Mass times acceleration due to gravity. So G is something as A. So you can use what you have on our acceleration. Use it here. So while force is work is force times distance also. Now, by the time you get the dimension for work, you will now agree with me that work and the moment of force, they have the same SI unit, and at the same time they have the same dimension. Okay, this is where we'll end the lesson today. Thank you for being there. Please make sure you subscribe to this channel. There is a like button there. Please hit that like button. Share this knowledge with your friends so that they will learn alongside with you. Thank you very much.